Okay, so this is the first lesson on complex numbers from AS Further Maths. So this lesson we're just going to introduce the idea of a complex number, look at a little bit of arithmetic with them, so adding, subtracting, multiplying and dividing. We're going to recap a bit about different types of numbers. So you've met a lot of different types of numbers already, which we're going to just quickly go over. The first and most basic type of numbers are the natural numbers. So we denote these with an n with a double bar on. And these are sometimes called the counting numbers. So these are 1, 2, 3, 4, 5, and so on. We're going to build up a diagram of these numbers. So on your diagram, if you can add in a circle with an n in the middle to represent the natural numbers. However, natural numbers can't solve everything. So there are some equations which we can't just use natural numbers for. For example, here we've got x plus 5 equals 2. You know that this solves to x is minus 3. So to solve things like this, we also need negative numbers or negative integers to be more specific. So we expand our set to include whole negative numbers. And this is the set called the integers. We use a z to represent this. And this includes the natural numbers, so it includes 1, 2, 3, 4, 5, and so on, but also has 0 and also negative. So on your diagram, draw a circle around n and including z as well. Now, again, this doesn't cover everything, so there are some equations which will require fractions to solve. So this one here, 2x minus 5 equals 0, will need 5 over 2. We then expand our set to include what we call a rational number. So we use a Q for quotient here with 2 lines on. This is any number that can be written as a fraction with integers on the numerator and denominator. This includes all of your integers and natural numbers, so this circle goes around n and z, and also includes q. However, we've still got equations which can't be solved by fractions, in which case we need irrational numbers. For example, x squared equals 2 has solution plus or minus root 2, which can't be written as a fraction. So classic irrational numbers are root 2 pi e. So we're going to expand this now to be the real numbers, which includes everything on the number line. And so far, up until now, this is all you know about. But there are still equations which we say have no real solutions. So things like these examples down here, we've got x squared equals minus 1. You'd say that has no real solutions because you try to square root a negative number. If you tried to solve x squared plus 4x plus 13 on your calculator, it'd say no real solutions because the discriminant is less than 0. Other equations where we say there's no real solutions, sine x equals 2, because we know sine x is between 1 and minus 1, and 2 to the x is minus 3 also has no real solutions because 2 to the x is positive for all real values of x. However, these can all be solved using what's called complex numbers. We're just going to look at solving 1 and 2 in the further maths course, but you can solve the other ones as well. Now, to deal with these, what happens when we try to solve them? For example, if we look at the first one, if you try to solve this, you square root both sides and you end up with x plus or minus root minus 1. Now, we say this has no real solutions because you can't square root minus 1. To solve this, we give this root minus 1 a name. So we're going to call root minus 1 the letter I, which is kind of better written as I squared equals minus 1. So you square both sides, you get minus 1. Okay. And whenever we now encounter a negative square root, we can write this as a real number times by I. So what I'd like you to have a go at now is pausing the video and solving equation 2 by hand, so using the formula or solving, completing the square. But when you end up with a negative square root, using I for that. Using completing the square, you end up square rooting minus 9. When you square root minus 9, you can write this using your thirds laws as root minus 1 times root 9. Root 9, you know, is 3. So this ends up with plus or minus 3i in your solution. Your calculator can work with complex numbers. So on your normal run matrix mode, if you go on setup, so shift and then menu, you can scroll down to where it says complex mode. This will probably currently be set to real on your calculator, but if you press F2, you can change this to A plus BI. And now if you try and solve equation 2 on your calculator, X squared plus 4x plus 13. Usually it would have said no real solutions, but now that we're working in complex mode, it will give you the complex solutions. So we can add this onto our diagram. So complex numbers, we define to be numbers of the form x plus I, y, or a plus b, I, or something like that. X and y have to be real numbers. They can have i's in them. And we're defining I with I squared equals minus 1. X is what we call the real part of z. So this is, we write this as re z equals x. Y is what we call the imaginary part of z. So we'd write im z equals y. Now, we normally use z for complex numbers. Notice that the imaginary part doesn't include the I, it's just the y value. If you've got y equals 0, yeah, z is just a real number. So real numbers are included in the complex numbers. And a slight difference between complex and imaginary numbers is that if x is 0, z is just iy. So we would say this is an imaginary number because it doesn't have any real part. We can now expand our number sets to have the complex numbers, which contains all of the real numbers and also all the complex numbers. So you can add a C on the outside of your diagram, and this is the definition. So we're going to look now at arithmetic with complex numbers, so adding, subtracting, multiplying, and so on. I'm going to work through the examples. Once I finish each section, you can pause the video and have a go at the U-Try questions in your pack. Addition of complex numbers hopefully works as you would expect it to work. It's just like collecting like terms. So here we've got two complex numbers, W and Z. We're looking at Z to start off with. So the real part of Z is 4 and the imaginary part of Z is minus 3. Note that doesn't include the I. And if you want to do W plus Z, this is 3 plus 2I plus 4 minus 3I. You collect up the real parts, which is 3 plus 4, which is 7. And you collect up the imaginary parts, which is 2I minus 3I, which gives you minus 9. If you multiply them by constants, it works as exactly as you would expect. So 2 times W, 2 times 3 plus 2I, minus 5 times Z, 5 times that. I'm going to expand the brackets out. So 6 plus 4I minus 20 plus 15I. And now collect up the real and imaginary parts. So 6 minus 20 gives me minus 14. And 4 plus 15 gives me 19i. Pause the video, have a go at the U-Tries. Next, on to multiplication of complex numbers. So this works just like expanding brackets. So doing W times Z, that's 2 plus 3i. Sorry, 3 plus 2i. 4 minus 3i. I'm just going to expand these brackets here. So 3 times 4 gives me 12, minus 9i, plus 8i, and then minus 6i squared. Now writing it as minus 6i squared makes me remember to do something with the I squared. I squared, remember, is minus 1. So minus 6i squared. If I squared is minus 1, this is equal to plus 6. And then when I'm collecting up my real parts, this is 12 plus 6 is 18. And minus 9 plus 8 gives me minus 9. For this next one, I've got IW, so that's I times 3 plus 2i plus 2z. I'm going to expand out the brackets again and then collect like terms. So I times 3 is 3i. I'm going to put plus 2i squared here. 2 times 4 is 8. And minus 6i. Remember, I squared is minus 1. So this 2i squared is equal to minus 2. Collecting up my real and imaginary parts, I've got minus 2 plus 8, which gives me 6. and then 3i minus 6i gives me minus 3i. Finally, for w squared, I need to do this as a double bracket. So this is 3 plus 2i times 3 plus 2i. This gives me 9 plus 6i plus 6i plus 4i squared. Remembering that I squared is minus 1, 4i squared is minus 4. So when I collect my real parts, I've got 9 minus 4, which is 5. And my imaginary parts are 6 plus 6, 12. Pause the video again, have a go at the U tries, and then I'll reveal the answers. Next, we're going to look at division of complex numbers. This works like rationalizing the denominator with surds. So I'm going to look at 1 over w first. 1 over w is 1 over 3 plus 2. To rationalize the denominator, or to make this into a complex number, a plus bi, I need to times top and bottom by the same thing, which is 3 minus 2i. So it's the same as this with the opposite sign in the middle. This is called the complex conjugate of a number. So when you change the sign in front of the I, it's the complex conjugate. The top is just 3 minus 2i. And on the bottom, I'm doing 3 times 3 is 9, minus 6i, plus 6i, minus 4i squared. Being careful with that because it's really easy to make mistakes. What should happen on your denominator is that your imaginary parts should cancel, and you're just left with a real number. Remember, 4i squared minus 4i squared, that's equal to plus 4. So yeah, we've got 3 over 13 minus 2 over 13. Notice I haven't written it all over 13. I've split it up into a real and imaginary part, which is quite often how they would like you to write your answers. For w over z, a little bit more work. So I've got 3 plus 2i over 4 minus 3i. Times in by the complex conjugate of z. On the top and bottom, it's 4 plus 3i. We're going to expand out the top and make a bit of room down here. So I get 12 plus 9i plus 8i plus 6i squared. And expand out the bottom, so 16 plus 12i minus 12i minus 9i squared. On your bottom, your imaginary parts should cancel. And remember, minus 9i squared is the same as plus 9. Also on the top, 6i squared is the same as minus 6. So now I can collect up my real parts on the top. 12 minus 6 gives me 6. My imaginary parts is 17i. And this is all over 25 on the bottom, or it's better if I write it as 6 over 25 plus 17 over 25. Right. Again, pause the video, have a go at the U tries, and I'll show the answers. Your calculator has the power to do all these calculations for you. However, in an exam, look up for the wording of the question. Quite often on Edexcel, they want to see all of your working. So especially if it's a show that question, or it says fully justify, or it says solutions relying on calculator technology are not acceptable, you should be showing your working for these types of questions. The final thing to look at is the complex conjugate of a number, which we've mentioned already. So if you've got a complex number z equals a plus bi, the complex conjugate we denote using a star. So this is z star is the complex conjugate. The real part is the same, but it's the imaginary part that you change the sign. So in this example here, we've got z is 2 minus 5i. Z star, the conjugate of that is 2 plus 5i. Couple of multiplications here. So Z star times W star, well, Z star is 2 plus 5i. W, we change the sign in front of the I, so that's -1 minus I. And then we're going to expand this as normal. So -2 minus 2i minus 5i minus 5i squared. Collect up your real and imaginary parts. So remember, -5i squared is plus 5. Combine that with the -2 gives us 3. And then putting your imaginary parts together, it gives us -7i. Underneath, we've got ZW all starred. So I'm going to do ZW first and then do the conjugate of that. So Z is 2 minus 5i. W is -1 plus I. And I'm going to multiply inside that bracket first. This is going to give me -2 plus 2i plus 5i minus 5i squared. Collecting up my real and imaginary parts in there. My real parts, -5i squared is plus 5. So again, that gives me 3 plus 7i for my imaginary parts. But then doing the conjugate of that changes the sign on that I. So you get 3 minus 7i. What you'll notice is that these two things are the same, which isn't a coincidence. It turns out that with conjugation, you can sort of expand the brackets out, although it doesn't work exactly the same as powers. So if you do multiplication, you can distribute the conjugate across the Z and the W, like this one here. So Z times W star is the same as Z star times W star. Works as well for division. And weirdly, it also works for addition and subtraction as well. So you can bring the star inside here and it's the same as Z star plus W star. But this isn't the same as how powers work. Pause the video, have a go at the final U try, and then I'll reveal the answer.